the acronym COMETS is what we use. It's a very small, loose club of meteorite enthusiasts, collectors, dealers. I don't know, maybe 30-some people around the region, and even a couple that are out of state. But we don't hold any regular meetings. We have our own Yahoo group, and that's how we communicate. So if anybody's interested, they can look up Colorado Meteorite Society on the Yahoo groups. And to join that club, all you have to do is join the Yahoo group. We have no dues, we have no officers, we have no rules.
No bylaws.
So, and we haven't even had a meeting for a while. So people get busy, and so nothing gets done. But periodically we have meetings. Occasionally we've even had speakers, but not very often.
I think one of the fun events is our annual barbecue and auction.
During the Denver Gem and Mineral Show, we hold a meteorite auction on the Friday of that week, and serve food and beer, and everybody that's interested in buying meteorites congregates there, and it's a good time. All the dealers from the show come, and the only bigger gathering in the country is the Tucson Gem and Mineral Show in February, and that's a very big gathering for the meteorite people from all over the world. So that's always a fun time. You're going to have to come sometime. Tucson.
Tucson is on my to-do list.
It's a dangerous place, though.
Well, that's what I'm afraid of. I'm afraid it will make my wallet a lot thinner.
Yes.
It's bad enough when I go to the rock and mineral shows here in the Denver area. Well, as you can see on the table, Dan and I brought in several specimens this evening, and we're going to pass some of these around for you to take a look at. So some of these are suitable for holding in your hands and looking at. Some of the bigger ones, particularly the irons, be careful when you handle them. They're not fragile, it's just that they're heavier than they look. And if you drop one, it's liable to do damage to your feet,
Toes are
your
risk.
toes, possibly chip wood surfaces and things, just because they are rather heavy. So we have a nice collection here this evening. And to get started with this, I think it makes sense to begin with some of the terminology of the science of meteoritics. And the first place to start is the language that you hear. You may hear people in the popular media talking about, oh look, there's a meteor. No, not quite. We start out with the first term that you should be familiar with, and that's meteoroid. Meteoroid is the rock that is zipping along through space at a fairly high rate of speed. And should that meteoroid enter our atmosphere, it will produce an atmospheric phenomenon, a streak of light that is sometimes, although incorrectly, called a shooting star. So the streak of light in the sky, typically you see these at night, but if the meteoroid is big enough, it can produce a meteor that is visible in the daylight hours. The meteor is just the streak of light. Now think about the word for a moment. Its origin goes back to the 1500s or 1600s. And at that time, the word meteor was used generally to represent just about any atmospheric phenomena. Lightning, rainbows, and of course, shooting stars were all known as meteors, an atmospheric phenomenon. And what's the title given to the weather person on television? Meteorologist. It's somebody who studies atmospheric phenomenon, specifically the weather.
In fact, they believed at one time that lightning caused rocks to fall from the sky.
That's true. It took a long time for scientists to accept the fact that meteorites are from space. They were believed to be volcanic in origin or produced in thunderstorms.
So-called civilized man was a long time in accepting that. Aboriginal tribes around the world, they knew better. They knew rocks fell from the sky. Ask the Australian Aborigines or some of the other Indian tribes. They were very sure about these things that fell from the sky, and they used them as venerated objects in their ceremonies.
Here's something that'll surprise you. When you see a meteor in the night sky, the odds are the meteoroid that produced that meteor is no bigger than a grain of sand to perhaps the size of a pea. The vast majority of meteors visible in the sky are produced by very, very small meteors. But understand that they're traveling at a very, very high velocity. anywhere from 20 to 30,000 miles an hour to over 120,000 miles per hour. Now there's one other piece. When you do see the shooting star or meteor in the night sky, it first becomes visible when the meteoroid is about 60 miles or so above the surface of the Earth.
When the light goes out, it's probably still 11 to 20 miles in the sky. Witnesses all the time say, oh, it just landed over on that hill. Oh, I saw the light. It quit, landed right over there. Well, no. It probably landed the next state away from you because it was so high in the sky, it kept going for quite a long distance.
Now, should the meteoroid be big enough and survive the plunge through Earth's atmosphere, once the meteor itself extinguishes, if you will, the meteoroid will go into what's sometimes called dark flight or cold flight, and will continue on, but at a much, much slower rate most of the time, typically slowing down to terminal velocity, so maybe a couple hundred miles an hour, at which point it falls to the Earth.
Basically, when it goes into the dark part of the flight, it has expended all of its excess speed from space, and basically at that point falls out of the sky. So the arc, whatever arc it was coming in on, changes radically and basically falls out of the sky and lands at terminal velocity, depending on the density of the object, somewhere around 300 miles an hour or less.
Do they make like ballistic paths or hyperbolas or parabolas?
It really depends on the angle that it comes in at, and the strewn field of any particles that are left as they spread out over the ground is also determined by the winds at the time. But they usually make an oval on the ground with the heaviest pieces going to the far end of that oval.
Lighter pieces falling to the ground first. Now, that brings us to the last term in the list of terminology, and that's meteorite. Should the meteoroid make it to the surface of the Earth? Here it is. It is called a meteorite. So feel free to pass this around. That is a stony meteorite that was found in the Sahara Desert in northwest Africa.
Most meteorites that fall on Earth are stony meteorites, the vast majority of them.
This one is not.
No, that's not a stony meteorite. You'll notice that's roughly the same size as the other one that's being passed around. This is an iron meteorite, and it's about twice as heavy as the stony meteorite that's leading it going around the room here.
One that'll break toes.
That'll break toes, turn your toes into pancakes or waffles.
I show meteorites all the time, and people say, "Oh, where'd it come from?" Well, outer space. But what they really mean is where was it found, or where did it land usually?
The vast majority of meteorites originate in the asteroid belt. The asteroid belt is located between the orbits of Mars and Jupiter. I do have to point something out here. You may remember the movie, I think it was The Empire Strikes Back, when Han Solo was trying to outrun the Star Destroyer through the asteroid field. Hollywood did take a little bit of liberty with that. At least in our asteroid belt, the asteroids are a bit farther apart than that. Any guesses on the average distance between asteroids in our asteroid belt?
They don't call it space for nothing.
Yeah.
That should be a hint.
It's gotta be thousands of kilometers.
Yeah.
It's about 100 miles. So roughly the distance between here and Cheyenne. That's
Really?
roughly the average distance between asteroids in the asteroid belt.
What's the average size?
And there are families or groups, so they're clumped. It isn't an even distribution.
It's an average.
This really kind of skews the view too. It's not that dense. So
I don't know what the average size is. My recollection is the mass of all of the asteroids in the asteroid belt combined is less than that of the moon.
wouldn't make a decent planet. No.
There's not enough mass there for that. The largest asteroid is Ceres. There's a space probe headed there as we speak. It just finished a year of orbits around Vesta 4 as it's sometimes called. And we do have some meteorite fragments up here from Vesta. That's one of the few asteroids that scientists have been able to associate with specific meteorites. I talk about the asteroid belt as being the source of most meteorites. There are a couple interesting exceptions, and they're fairly rare. One is lunar, and the other is Martian. And what that means is those are meteorites that came from the moon and came from Mars.
How do you know?
That's a good question, and I'm going to answer that later. We've got a, now seriously, scientists do have a way to figure that out. I'm going to pass these two guys around. You'll notice that there are a couple small specimens here. I normally don't bring these to our open houses and public nights. They're a little bigger than the little ones that I usually bring. But there is a piece of lunar here and a piece of Martian here. So take a
People
look.
always want to know, they think all meteorites are worth a lot of money. Well, most of them aren't worth that much, except for lunar and Martians.
Yes.
And lunar meteorites are about the most expensive thing that you can find on Earth, generally selling for $1,000 or more dollars a gram.
That's a gram.
What about other planets or even stony moons?
There's one meteorite that some scientists think might be from Mercury, but the jury is still out on that. And then other than that,
The orbital physicists tell us that we should have meteorites from Mercury and possibly from Venus, but you'd have to overcome a lot of gravity to get a piece off of Venus. So we don't know enough about Mercury yet. We don't. We know a little more now that we have an orbital probe up there, but we haven't been down to the surface, so we don't know any of the chemistry yet, unlike Mars and the Moon, where we do know that. So there's a possibility that we could have Mercurian meteorites in our collections and not know it yet. There are some pretty weird things that we haven't associated with anything else yet. So
okay.
time will tell.
It's probably good to talk a little bit about meteor showers. I think most of you are probably familiar with those. You go out, take the August Perseid shower and sit back on a lawn chair under a hopefully reasonably dark sky and watch the night sky fill up with shooting stars. The meteor shower occurs when the Earth passes through a trail of debris left behind by a passing comet. So the debris is very small, typically dust-sized to maybe no bigger than the size of a pea. But it's pieces of ice, pieces of dust, and small pieces of gravel. And many comets that orbit the sun in the solar system are Earth-crossing, or have been at some point in the past, and they've left trails of debris across Earth's orbit. And as the Earth plows into this trail of debris, we see these shooting stars or meteors as a meteor shower.
The solar wind pushes some of the trails our way too.
That helps, because some of the original trails do get moved away because it's dust and tiny sand-sized pieces to pea-sized pieces, so it doesn't take much to move that stuff around. Scientists know of over 60 confirmed meteor showers, and there are a couple hundred others that are under study right now. And I say under study because in many cases those uncertain ones may only produce a very, very slight increase above the normal background meteor rate. The meteor showers are typically named after the constellation from which they appear to originate. You look in the night sky during a meteor shower and you'll see that one went that way, one went that way, one went that way. And if you backtrack all those, they all go back to a point called the radian, which is typically located within a constellation that is applied to the name of the shower. Question?
At what point does it cross over from background meteors to a meteor shower?
Well, that's where there's some uncertainty in the study here, because the background rate can also vary. The background rate varies, particularly time of day. In the daytime, you're not going to see them, but radio signals can be bounced off the trails, that is, the meteors left behind. But as the Earth rotates around through darkness at night, and it's zipping along through its orbit around the sun, the part that faces head-on, driving into the direction of the travel of the Earth around the sun, that's when the rates tend to increase somewhat, and as you go away from that, then they tend to decrease. So I don't know if there's an average half a dozen per hour maybe maybe a little bit less might be the background rate. But again, it's going to vary depending on time of day. The 6 in the morning-ish, kind of midnight to 6 a.m. to noon is probably the best time for meteors because we tend to be plowing head on. It's like driving into a snowstorm or driving into the rain as the raindrops hit the windshield versus away from it, you look out the back window and you don't see that stuff hitting the windshield. So it's the same thing with the Earth.
So the sporadics, they come from the particles that make up the zodiacal light or the gaming shine? See, the zodiacal...
That's pretty fine stuff, probably not. That's really fine material, yeah. They're just odd pieces that, you know,
A lot of
who knows
pieces.
where they've come from. But the other point is there are no known meteorites to have occurred from meteor showers. This material is all of the size that it burns up on the way in, and there's never been anything collected from a meteor shower.
That's something that surprises a lot of people. They think, oh, gee, they get a meteorite whacking the ground during the Perseids. It must have been part of the shower. Well, no, it was a sporadic that happened to hit the Earth, become a meteorite, and it had nothing to do other than coincidence.
Now, one thing astronomical that you can do during a meteor shower, and there is a group of people doing that, is to look at the non-illuminated portion of the moon if it occurs, you know, if it's full moon, there's no dice, but if there's a partial phase of the moon, you can train your telescopes on the darkened portion and observe and possibly photograph strikes from meteor showers on the moon.
No atmosphere there to burn.
And there have been a number of images taken over the years.
There's a table that I put together of a handful of the very popular meteor showers. There's something else that some people do during meteor showers. I'm a ham radio operator. Any other ham operators in here? Some of us in the ham radio hobby like to partake a form of communications known as meteor scatter. The meteor scatter involves pointing an antenna kind of in a northerly direction, more or less, and sometimes other directions, but bouncing radio waves off of the meteors, that is, the trails left behind. Because not only does the meteoroid produce visible light, more often than not, I mean, sometimes it doesn't, but more often than not it produces visible light, it also ionizes a column of the atmosphere. And while that ionization exists, radio waves can bounce off of the trail left behind by the meteoroid. And during meteor showers, it can be a lot of fun. Most ham operators that do that, you typically use a high-speed data communications that, in conjunction with some digital signal processing, allows them to pull some very, very weak signals off of the reflections. Now, I remember during the Leonid storm in kind of 2000-ish time frame, I took the Jeep that I had at the time and tuned into the what's called the 6-meter ham band, which is around 50 megahertz, and listened to ham operators around the country communicating by voice on the meteor shower, because there were so many meteors during that storm that it provided continuous communications, or nearly continuous communications, which is almost impossible otherwise using meteor scatter. So that's another interesting thing that can be done with meteors. All right, here we get into the fun stuff. Kinds of meteorites. They are generally broken down into 3 categories. One is stony meteorites, and we passed one of those around the room. And the other is iron meteorites. And take a look at the picture. You say, well, that's what I think of when I think of meteorites. You see those in museums, you know, a big piece of iron. It's got all these little dents in it. The dents, by the way, are nicknamed thumbprints. The official name is Hranac. But that's formed by material ablating off the surface of the meteoroid as it's plunging through the atmosphere.
One well-known iron meteorite fall occurred in Russia. It's called Chamberlin, and it was in 1947, and there were tons of that material collected. It's still being collected. I've collected a whole Riker amount here of little tiny cicoats because it broke up and is what we call shrapnel. Although some of these pieces are not, some of these are regular little pieces with lips on them, but I'll pass around all kinds of very, very interesting shapes. I've had fun finding these, hunting through pounds of this material at the Denver Mineral Shows.
The third general type is what's called a stony iron. Stony iron meteorite's a combination of a stony meteorite and an iron meteorite. And it's kind of hard to tell from this picture, but you may recognize these two people from the television program on the Science Channel. It's Jeff Notkin and Steve Arnold from the Meteorite Men. And Jeff, well, both of them are dealers. Jeff is down in Tucson with a company called Aerolite Meteorites, and Steve has a shop in, remember the town? It's in Arkansas.
Somewhere in Arkansas.
I can't remember the name of his store, but he sells meteorites too. So if you are interested in collecting meteorites, both of these guys are available to purchase your meteorites from. This one is a huge stony iron, and we'll show you some examples of this.
The oldest material are the stony meteorites, what we call the chondrites. They're called chondrites because they're made up of small little BBs of material called chondrules, and they're mostly silicates that coalesced out of the solar nebula at the beginning of the solar system. So those is actually a little bit older than the other materials by a small amount, because that's very, very primitive material from the beginning of the solar system. The other two forms, stony irons and irons, are from a failed planetoid, where it's what we call a differentiated body, where there was enough heat to melt the metals and cause them to sink to the middle of the planetoid, and then it was later destroyed. So when you see an iron, you're seeing the center of a failed planetoid. When you see a stony iron, you're seeing mantle material from that same type of body.
And I've got in this Riker mount three pieces, three slices that show examples of each of these. The top one is a slice of iron meteorite, specifically the Campo del Cielo from Argentina. The next one is Russian meteorite. It is a pallasite meteorite. Question, anybody in here have a birthday in August? Your birthstone is in this stony iron. It's called olivine. Of course, the gemstone variety of olivine is peridot or peridot, but the mineral itself is known as olivine. And there's some olivine crystals in this piece, so we'll pass this around. And then the bottom one is the stony meteorite, and you can see the chondrules, and if you turn it just right, you can see little flecks of metal like glitter. That's the iron nickel that's in there, although the stony meteorite is mostly rock. It does have some little flecks of iron nickel in it. And then you'll see the iron, of course, like the real heavy one that went around, it's almost all iron.
Yes, David?
Do they vaporize different when they go through the atmosphere? I mean, just to look at them, the iron.
There are certain meteorites, there's a type we haven't talked about yet, a carbonaceous chondrite. They're very friable. They don't hold up well coming through the atmosphere. Of course, irons, that's the densest and it holds up really well. A lot of the stonies tend to break up, easier than the irons. And the pallasites and mesositerites, yeah, it just depends. Some of them are stronger than others, others are weaker, and yeah, there's some variability in that.
That stony looks like it's survived a lot better than the iron.
Yeah, although some of them do break up. We get to thank our atmosphere for protecting us, because otherwise we'd have rocks falling on our heads all the time. Most of the material does not go through the atmosphere.
Remember, Hudson, we do have rocks all the time, they're just small.
Sorry?
We do have rocks.
There's dust, a lot of it's reduced to dust, which falls on Earth, and I think you have a point where in those programs where you talk about how much material agglomerates to Earth yearly.
I don't know if the color is going to give away that it's a stony meteorite or an iron or a stony iron. I think that may be more related to the composition of the minerals that are ablating from the meteoroid, and also their interaction with the Earth's atmosphere.
I saw one that was recovered up in Blue Lake, California, and it was white. It was neon.
Well, that would indicate a lot of olivine content. There are diogenite is a form of meteorite that has a lot of olivine, and some of those are green. Yeah.
Looks very glass.
So a half-foot chunk.
You're mostly when you get a fresh fall, the fusion crust is very black. On certain types of meteorites, even shiny black, and very fresh. And
I've got some pieces to show you. I think a lot of people in here have seen before the little pea sizers.
the big Russian fall a year ago, over a year ago.
And if you look closely at that, you'll see that the fusion crust is black like charcoal. And the stony meteorite that went around earlier, you'll notice that it's turned kind of brown. It's oxidized over time. It still has a visible fusion crust. If you look at it closely, you can see the fusion crust. You can see secondary fusion crust where a piece broke off during flight through the atmosphere and it started to melt the break. And then you can see where it broke off after the impact, and then of course it's weathered a lot from sitting in the desert. But when they're fresh, they're just charcoal.
When meteorites are classified, they're given a weathering grade, and 0 would be very fresh, and it goes up from there. And some of the meteorites have been on Earth for a really, really long time, and they're what we call terrestrialized, particularly irons change into limonite. And some of the other meteorites, the iron has oxidized to the point where there's just hardly any iron left in it. Wolf Creek is one I think can think of. Australia, that's very terrestrialized material.
The one on the right is I think that's is that Brenham?
That's probably Brenham. Yeah.
This is a really nice palisade on the inside. They dug this up from.
It's been in the ground a long time, so very rusty.
It's real rusty on the outside, real weathered on the outside. So it's got a layer of just grunge on the outside, but you get inside of it, it's gorgeous with the iron nickel matrix and the olivine crystals.
Yeah, I was just going to say, you would think that the nickel irons would be very strong and hold together a lot better, and yet Sakota-Alim just apparently came apart into a bunch of like buckshot.
It's hard to imagine the hardness of our atmosphere.
Yes.
When something's coming in at 35, 40,000 miles an hour and hits our atmosphere, it's like hitting a brick wall.
Yeah.
And so these forces can actually tear a solid object, iron object apart like artillery shrapnel. It is kind of mind-boggling.
Yeah, obviously it did.
The Sakota-Alim, it's been said that there were probably at least 2 airbursts, 2 explosions in the air. One that produced the traditional-looking meteorite pieces with the regma blips, and then the other that produced the shrapnel that looks like literally like a bomb went off. So Sakota-Alim is available in both of those types. The other one that is that was created by an airburst is the Campo del Cielo from Argentina. That one also exploded in the atmosphere, and the fragments showered to the ground and formed a stream field that's about 12 miles long and a couple miles wide, and several craters. And there were tons of that have been brought out of Argentina.
When the Spaniards entered Argentina the first time, the Indians showed them where this material was, that there's tons of that material still in existence.
Does anybody in here speak Spanish? Campo del Cielo, field of the sky. When the Spaniards came through in the 1500s, the indigenous people knew of this as rocks or stones from heaven. So it's likely that when the impact occurred about 4,500 to 5,000 years ago, that it was witnessed. Okay, kinds of meteorites. That's your slide, so take it away, Dan.
Well, yeah, we start out with the dust cloud that we have that formed our solar system, the protoplanetary cloud, and it starts to condense. The condensing action starts with static electricity, actually, and starts agglomerating these small particles that we call chondrules now. And eventually, particles get big enough and agglomerate enough, gravity starts to kick in and starts more accretion. So that material will turn in eventually into a protoplanetary object of some kind. And there were a lot of collisions happening back then. So even with Earth, we know that probably the moon was created from Earth material by a large collision. And so a lot of these happened and broke things up, and they put it back together, and they broke up again. So there was a lot of that going on. Also, when enough material gathered together to form a planet, you also have the radioactive melting that occurs. Not only do you have all the energy from all the impacts, but you also have all the radioactivity from aluminum, what's the isotope?
26.
Okay. And other things that were heating things up quite a bit in those days. So all of that heating caused these planets to differentiate, with the lighter material forming the surface and the heavier material going to the middle. So Then you get your collisions again later on, failed planetoids that give you the different types of meteorites that we're going to talk about here in a little bit.
You say you're getting stonies, or the irons come from cores.
Right.
The stonies come from mantle. Any crust?
Stonies don't even come from mammals. Stonies come, they're original material that has not been differentiated. So it's never been heated or metamorphosed. Actually, some slight metamorphosed chondrules, it does take place in them. So when we classify chondrites, we give them, first of all, it's either an H, or it means high metal, an L for low metal, or LL for low, and then we give them a number. And that number, it's a weird system, but a 3, an H3 would be very pristine chondrules that have not been metamorphosed. They're gorgeous. They're all intact. And then as the numbers go up, 4, 5, 6, and there's even a theoretical 7. By the time you get to 6, you'll have a hard time finding an attack chondrule in a stony meteorite. So there's been enough heat and other actions on it over time to get rid of the chondrules, to metamorphose them away. There's also some theoretical, because it starts at 3, there is some alteration that can be caused, hydrous alteration in some forms of meteorites that would give you a 2. But that's getting a little technical.
Water?
Yeah, yes.
Yeah.
In their stellar,
Yes.
in their stellar
Yes.
class.
There's a lot of water up there.
Right. So you're not getting any crust action though. You're getting mantle or.
Right.
The stony irons are believed to be from that mantle crust area, but there's another bit of thought out there that stony irons may have also been formed by really energetic impacts.
Wow.
And may not have been from mantle material. That's one of the theories that's being debated.
There are meteorites that are soil, which is what you get on the surface.
Crust, basically.
Granitic source.
When we talk about the stuff from Vesta, that's basically soil material. It's been crushed and altered in a lot of ways. So, regolith, they call it. David?
Is the stuff from the Oort cloud different than the stuff that normal meteorites are?
Well, what are we getting for the Oort cloud? We're getting
Comets.
comets. Is all we're getting.
It's all
Ice mostly.
And we haven't sent any probes up there to take a close look. We're soon going to get a close look at Ceres. We're learning a little more and more each time we get to look at one of the asteroids. The look that we took at Vesta confirmed what we already had ascertained through spectrographic studies from large telescopes on Earth, that the HEDs, the Howardites, Eucrites, and Diogenites that we collected in meteorites were definitely material from the Vesta group. And that was confirmed by the close-up studies.
Here's a Riker mount with samples of each of the HED meteorites from Vesta. There are a lot of others besides these, but this will give you an idea of what these look like. And take a look at the slice here, and you'll see what Dan was talking about with respect to this regolith type composition. Scientists were able to identify Vesta as the source of the HED meteorites by taking meteorites like this and grinding them up into powder and then doing reflectance spectroscopy measurements, plotting the light curve, and then comparing that with the reflected light curve from Vesta. The interesting thing is Vesta's position in the asteroid belt is such that it would be very, very difficult for meteorites to have originated right from Vesta. However, when the space probe got close enough to Vesta to get really nice images, they confirmed that a good chunk of the southern hemisphere of Vesta had been blasted away by an impact, and I want to say it's a 250 kilometer crater or something. It's huge. There's a group of asteroids within the asteroid belt called Vestoids that are believed to have been liberated from Vesta by a collision at some point in the past. And their position in the asteroid belt such that gravitational perturbations can knock them out of the asteroid belt into Earth-crossing orbits. But they have the same composition as Vesta, so they're believed to have come from that impact that's liberated.
Some of these asteroids we suspect are basically rubble piles
Yeah.
that are just loosely held together by gravity.
So the impact that knocked that chunk off of Vesta, it didn't go into paint left over from the object that hit it?
They've been looking for the paint on the bumper on the other asteroids and haven't seen
Yeah, I'm
it.
just going to say that you run into a problem of contamination. Whatever knocked it off
Right.
would be adding its stuff to it. So.
Right.
Yeah.
And that's the classification of some of those meteorites. Some of those are agglomerations of several things.
Right,
That's what
sure.
makes the classification. So,
Now, speaking of classification, here's one way that they're classified. And you recall from a few minutes ago, I said that meteorites in general are grouped into three areas. The irons, the stonies, and the stony irons. And then you can see underneath each one the unmelted, that would be the chondrites, the ordinary high and low iron, as well as carbonaceous chondrites. And then the irons and stony irons over here, and then there's also a category of stonies that fall into this melted category. So here you've got the achondrites, there's the HEDs from Vesta, the lunar and Martian meteorites that we'll talk about a little bit later. The iron meteorites here, the hexahedrites, octahedrites, and ataxites. The ataxites are kind of cool because they don't have the Wittgenstein pattern, that crisscross pattern that you see.
very
in
high
the
nickel
slice.
content.
And then mesositerites and pallasites, which are the stony irons. And the pallasites would be the example of the one that's in the one display case that has the olivine crystals. That is a pallasite. And there's another way to classify meteorites. This is from a research paper, and I just put it up here because it's an eye chart. There will be a test afterwards, so you can see that.
You can't read the
No,
thing.
you can't read this, but you can see that scientists can really get into some in-depth, very, very, very detailed classifications in the study of meteoritics.
I'll pass one around here. This is, when this was found in Russia, it was thought to be the most fabulous mesoceterite that was ever found. And I remember one Colorado dealer that had it. He was all excited about it. The spring show took me out to his truck to show it to me. Upon further study, it's been determined that this is iron and nickel and a basalt matrix. It's native iron. This makes this a very rare mineral specimen. It's not a meteorite. It looks like a meteorite. It looks like a mesoceterite, but it's from Purana Plateau, Russia, found in August of '84. And if you want to know what a mesoceterite looks like, a great one, this is a great looking one, but it's not. So it's a meteor-wrong,
terrestrial, yeah.
but this will always be in my collection because I've still been trying to get other samples of native iron. Native iron does not exist on Earth in this form.
It's very, very
All of
rare.
our iron on Earth is in sulfides or mixed in with other things.
Iron oil.
And so there's no pure iron. And if we got down to the mantle, you'd find this stuff, but you don't find it on the surface. There's some from Russia, some from Greenland, and one supposed it's one from Oregon. But this is really, really rare stuff, and I've been trying to get my hands on some of the Greenland material, and it's expensive, and nobody seems to have it every time I go looking for it.
Unobtainium.
Yeah. But this is neat stuff,
Yeah.
but not a meteorite.
All right.
Sure looks like one.
Well, what's inside the meteorite? I passed around the one Riker mount that shows the three slices of stony, the iron, and the stony iron. The Campo del Cielo, the real heavy one that was passed around in the beginning of the presentation, is an iron meteorite, and it's roughly 92% iron, about 6.5% nickel, a little less than 0.5% cobalt, 0.25% phosphorus, and then the rest of the stuff is in parts per million. Gallium, germanium, and iridium. So there's nothing mysterious or secret or anything in there, but that's pretty much it. And it's mostly iron. Now, if you take a magnet, this is the kind of magnet that you can use to, if you're working on your car and you drop a screw or something down in the engine compartment, you reach down and grab it with this. But these also work really well for those of us who like
We've got
rocks
a
and minerals.
few screws loose around here.
And you can see that it sticks to this iron meteorite because it's mostly iron.
By the way, that's how we hunt for meteorites, and I meant to bring my stick today, and I didn't bring it. I have a golf club handle with a very strong magnet on the end, so when you're hunting meteorites, you don't have to bend down and pick up every black rock you see. So all meteorites, except for rare forms, are magnetic. So any of them that you're going to find are magnetic. People will go, wow, what about the rare ones? You're not going to find a common one, let alone a rare one, so forget about that.
I thought more were stony.
Dina, do you have a question?
So based on what you said about the sample from Russia that they thought was a meteorite but
Right.
turned out not to be,
Right.
I take it it's not very likely if you're using your magnet along the ground that if it picks something up, it's not very likely to be a naturally occurring.
In Colorado, it is.
It is.
Yeah, you're going to get lots of magnetite and maybe some hematite.
Okay.
So that's just your first clue, is the magnetism.
Okay.
But it is also pretty much a deal breaker. If the rock is not magnetic, then it's not going to be a
But the
meteorite.
vast majority of rocks are not magnetic, right?
There are a lot of terrestrial rocks that
Didn't-
are attracted to magnets, but there are a lot more that aren't.
Did not hear you say that most meteorites are stony?
Yes, and they still have nickel iron in them. And you can still detect them with a metal detector, and you can still, magnet will still stick to them.
Think of it this way: the iron meteorites will have 90-ish% iron content, and it's pretty much all metal or mostly metal. The stony meteorites are rock; they're mostly silicates, and they might have anywhere from just a few percent iron
This is
nickel
a low
up to
metal
maybe
content.
20%.
Stony. So try it. Not put it on there. But it still sticks. This is an LL. So there's not a lot of iron in it. There's still iron in it.
Sort of my generic question is, if you have meteorites that you know are from Mars and from the moon, they knocked material off of those objects, whereas most of the meteorite material comes from different processes or whatever, from planet forming. Well, that process isn't that, so why would it be classified the same? Meaning, I can theoretically think of a big explosion, something hitting the Earth and knocking chunks of aluminum. And I would think if you hit the moon that you would probably hit aluminum off into space. Why isn't there aluminum content in lunar meteor?
There is a little. And there's also, I've seen native copper in meteorites. And there's gold.
Okay.
And I was going
And
to...
diamonds.
Yeah, and I don't have a slide. I need to do a slide that shows all the minerals in meteorites. It's quite extensive.
Yeah, because I would think that
Yeah.
things that
Yeah. What we're getting off of Mars and the moon are mostly basalts.
And they are not attracted to a magnet,
Well,
generally.
generally, some basalts are magnetic, some are not. So that's another terrestrial rock that can be magnetic as a basalt.
I'm going to pass this little guy around. It's not in a Riker mount, so make sure that it gets passed around and don't lose it. This is a slice of the Canyon Diablo meteorite from Meteor Crater in Arizona. And I mentioned that one of the things in some meteorites is diamonds. The Canyon Diablo meteorite does have what are called nanodiamonds. Now that doesn't mean you can go to your favorite jeweler and have a ring made out of the diamonds in this. These are things you might see with an electron microscope. The downside to the nanodiamonds in a meteorite like Canyon Diablo is that it is a bear to cut. It is just brutal on rock saws and
I've
other
seen when
things.
they were cut, the saw actually jumped.
Yeah.
And you can ruin a blade. Uralites are a type of meteorite that has a lot of diamonds in them. And most dealers that have cut them say they will never do it again because they went through a fortune in blades trying to cut it.
They're hard. This, don't worry about getting fingerprints on this. I bought this from a dealer several years ago at one of the rock and mineral shows because somebody covered it up with polyurethane or lacquer or something, which is the worst thing you can do with a meteorite. You'll notice as you look on the back that it's got quite a bit of rust that's forming because there's moisture in in the specimen, and of course it got trapped in there by the shellac or lac or whatever was put on here. But going the other way, you can touch this without worrying about leaving fingerprints on the.
I'm also going to send around, this is a piece of NWA 869, and there's a lot of this material, so it's pretty cheap, but this is one hell of a meteorite. This is a really, really good stony meteorite. I love it. It's a breccia, so it has broken pieces that are agglomerated together. It has a lot of inclusions, and you can see the chondrules, and you can see the metal content, and you can see the fusion crust, and you can see the fusion crust is less than a millimeter thick. So this is really, I love that stuff. There's a lot of it around. It's pretty cheap. It would be a real expensive meteorite if it was less of it around, because it is so nice.
The Riker's box that went around earlier with the three types, the stony, the iron, and the stony iron. The stony in that one is also NWA 869. Okay, here's what some of these things look like on the inside. And there's a close-up shot of a slice of a chondrule, and you can see, or chondrite rather, you can see the chondrules in that. You can see the little spherical chondrules in this slice of stony meteorite. And as Dan said earlier, those chondrules were formed in the early part of the solar system when dust had accreted to form these little spheres, were molten at the time, and then they solidified, and then those later accreted into larger bodies. So these things, you can
They're
figure,
silicates, they're olivines, pyroxenes mostly.
they're on the order of 4.5 to 4.6 billion years old.
Now, the iridium, it's 3.6 parts per million. What is its, how much of it do you find on Earth naturally, or do you find it, I mean, because that's the...
There is not much found on Earth.
It's very rare on Earth.
In fact, that's, that's
the iridium layer.
That's how we're, you got the iridium layer at certain boundaries, and that's from a large strike, the meteoritic material.
One of the bits of evidence for the extinction of the dinosaurs that kind of was a smoking gun was at what used to be called the KT boundary, the Cretaceous Tertiary boundary. Scientists have given those other names now, but I'm still calling it the KT boundary. I think a lot of the old timers will continue to call it the KT boundary, but within that is a layer of clay that's what, inch-ish thick,
Yeah.
and the iridium is reasonably high in there. And in the rock below the KT boundary, where that iridium layer is, a lot of fossils, of all kinds. And then above the KT boundary, it's like somebody flipped off a switch. And that was when the dinosaurs went extinct, was about 65 million years ago. That's about the age of that KT boundary. And at one time, scientists were leaning toward volcanism and other things as being the cause of the extinction of the dinosaurs. And that probably did contribute to it some. But the real evidence for an impact by a space object is that the high iridium content in the KT boundary layer. It's because iridium is common. Now you see it's in parts per million, but common in meteorites, asteroids, comets, but very, very rare on Earth.
So in an Earth rock, you wouldn't find parts per billion?
Maybe.
Maybe.
Yeah. Now
Okay, I've got another question. In the early 70s, there was this meteor that went, hit up near, well, it didn't hit. It came into the atmosphere up near.
Just went over the hill.
Nebraska?
Oh, yeah, 173.
Oh, I remember that one.
Across
Yeah.
Washington and Oregon.
And, yeah, it skipped through the atmosphere and then went back out.
Yes.
Now, if this beastie were to come back and end up on the ground, or parts of it end up on the ground, that would be kind of an interesting combination of factors there.
It would. I saw that one that you're referring to. It was in August of '73, somewhere around there.
Yeah,
There's a really nice video of the thing taken in the Grand Tetons in
Yeah.
Wyoming that shows it going from left to right on the screen. I was living in northern Idaho at the time and was riding a motorcycle with a friend of mine and saw this thing start on the southern horizon with what looked like flames or sparkles coming off the back. I thought, darn, it looks like an airplane on fire. So I stopped and turned off the motorcycle and listened, didn't hear a thing. And this thing went from the southern horizon across the sky to the northern horizon with, in daytime, with stuff sparkling off the back of it. And I had no idea what it was. until the next day. Then in the news, they said that this was, I think they called it in the newspaper a bolide, but it was a chunk of asteroid that had entered the Earth's atmosphere at a very, very shallow angle and had skimmed the upper layers of the Earth's atmosphere and then
Skimmed
gone
off the atmosphere.
back
Yeah.
into space.
Yeah.
So it wasn't seen just in Idaho and Wyoming, it was seen in 9 states and Canada. So it produced a pretty spectacular meteor. So that would, the visible object in the daytime is a meteor. That trail is a meteor, it's a visible meteor, because the object is probably fairly good sized.
Yeah.
But that was impressive to see.
We call the big ones bolides.
Yeah, that's what they called it. I remember seeing that in the newspaper
Yeah.
the next day.
But like I said, if that thing were to return and part of it actually strike the Earth, I think it would be interesting.
Well, we'll talk about a strike, not a near strike, here in a little bit. Take a look at this picture of the iron meteorite, and we've passed around a couple pieces already. You'll notice that this has kind of a crisscross pattern in it. That's called the Wittgenstein pattern. It's named after the scientist who discovered it. You don't find that in earth rocks. But take iron meteorites, not all of them, but most iron meteorites, slice them, polish them, etch them with nitric acid or some other etching material, and it brings out the crystalline structure of the iron nickel. And it's really pretty. It's like a fingerprint. Different iron meteorites have different patterns. You'll notice in the Rikers Mound that had the Campo del Cielo in it, the slice of Campo del Cielo that Wittgenstein had is really almost chaotic and disorganized. But in the little piece of Canyon Diablo that's going around, it's got a real nice crisscross pattern. This one has a real nice crisscross pattern, but they're really cool.
They're classified coarse, medium, and fine octahedrite patterns in the crystal structure. Yes, Kathy?
In some of the jewelry you've seen with that pattern on it, like in the gems, they call it Gibeon meteorites?
Yeah, Gibeon is a fine octahedrite. It has a very nice fine structure.
And it's got a bit higher nickel content, so it tends to be more stable and not want to rust.
So from the crystal size, can you estimate the cooling rate?
Well, it's related to the cooling rate. I'll leave it up to the geologist to estimate the cooling rates. But yes, the size of the crystal structure is related to the cooling rate. And for those of you who might be wondering what we're talking about, if you take any kind of molten material, or molten rock, or lava or magma or something, as it cools, it will form crystals. Go to Hawaii, for instance, if you see the lava on the Big Island in Volcanoes National Park, you look at it and you say it looks pretty bland and pretty ordinary, but if you put it under an electron microscope, you will see microscopic crystals. Now, go down to the Pikes Peak area, which is largely granite. That area, or the granite, has crystalline structure. You'll see the feldspar and the other minerals that are in the granite. That's actually the crystalline form of those things. So that's what's called an intrusive igneous rock, granite is. And it forms underground and cooled very, very, very slowly underground, which gave the crystals time to grow. So the same thing is true in meteorites. We can see in the crystalline structure here, the size of that would be related to the cooling rate. So it may take millions of years for it to cool in the core of a differentiated body. And as it does, the crystalline structure grows. The faster it cools, the smaller the crystalline structure, the slower it cools, the bigger the crystalline structure.
These iron blobs that are floating through space, especially the one that whacked Diablo, it's like we got a piece of the M&S, it's like almost 70 feet across of solid iron. Is that something that big, is that coming out of the supernova explosions? When a star dies when it makes iron, or is
So
that?
that was
out of the asteroid
that
belt.
was the asteroid belt. That used to be part of the core of an asteroid.
It was created,
Yeah, the iron comes from supernovae.
Yeah,
created there.
but it
It was probably made.
No, iron is created in a regular solar process.
Also into supernovae core. That's what
No,
causes them to collapse and
You can't get
explode.
beyond iron unless you have a
Yeah.
supernova explosion.
right. But in the case of the iron meteorites, those originated in our solar
Right.
system from the cores of differentiated asteroids. But yeah, before that,
But that's where it got the
it
iron.
originally came from a supernova somewhere, which formed the iron atoms and ultimately made its way to our solar system. Okay, there's the last one on the right, the stony iron. And Daryl, there's your birthstone again, the olivine crystals. You'll notice, and if you looked at the one that was passed around, that they're very fractured, very, very highly fractured. See, these are all broken. That's from impacts in space, in the asteroid belt. There are some stony iron meteorites that have unbroken olivine crystals in them. They're fairly rare, and they're extremely valuable. They make jewelry out of them, much like you can go to the department store and buy some earrings or a necklace or something that's made out of peridot. That's about $60 a carat. The olivine that comes from unfractured crystals in meteorites is about $5,000 a carat. But they are out there. Now, we've been talking about impacts, and certainly if you've ever looked at the moon through a telescope or binoculars, you have seen craters on the moon. So there's a lot of evidence of impacts on the moon, on Mercury, on Mars. Some of the asteroids and comets have evidence of impacts. So there's a lot of evidence of impacts out there. What about the Earth? You look at the moon and say, that thing's been whacked a bunch, but has the Earth been whacked a bunch? And the answer is yes. So where's the evidence? What happened to it?
Luckily, just not lately.
Yeah. Fortunately, those are very old impacts, but what happened to the evidence of impacts on Earth? Well, yeah, it was volcanism, erosion, wind, ice, water, tectonic plate movement, all that stuff is hidden or destroyed most of them. There's a photograph I took of Meteor Crater in Arizona. Neat place if you've never been there. It's about 40 or 45 miles east of Flagstaff. It's near Winslow. It's just off of Interstate 40. This is one of those deals where I just took the camera and went click, 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 and then did the software stitch it all together. This thing is 3/4 of a mile wide and about 600 feet deep. Scientists know of about 180 or so impact craters on the Earth. This is arguably the most famous one. Interesting story behind that. A fellow named Barringer, was it Daniel Barringer? I'm trying to remember his first name. Anyway, a fellow named Barringer, late 1800s, early 1900s, once they figured out that this wasn't volcanic, because at the time geologists thought, well, this is probably created by a steam explosion, because Flagstaff, as you may know, is a volcanic area. And they thought, this being only 40 or so miles away, it might be related to that. Once they determined that it was created by an impact, Barringer spent his fortune, literally spent his fortune over a period of years, digging mine shafts and drilling, thinking that there was a big chunk of iron in there that would make him even richer. And lo and behold, he didn't find really anything in there.
How ironic.
Yeah, yes, very ironic, right? There are pieces of the meteorite in the desert around the crater. Also, not far from the rim, there are little BB-sized pieces left over.
Turns out most of it vaporized on impact. And you can find it as little BBs of material for miles around the crater. Harvey Neininger proved where the missing mass was.
That was one of those situations where the Earth's atmosphere really didn't do much to slow that chunk of rock down. Iron.
It was big enough and fast enough.
It was big enough and fast enough. I think what I remember seeing in the museum at the crater, I think they figured the meteoroid, or maybe a small asteroid would be better, hit the desert probably going about 40,000 miles an hour. It just plowed straight in, and the energy was so great that it vaporized on it. Pieces of
driving by there, because just for miles you'll just see flat, and then they'll just be this huge sucker out there.
Yeah.
Just all over.
Yeah, it's pretty cool. So we do have craters, about 180 craters that are evidence of impacts on the Earth. These are cool, impactites. Dan, you want to take it away? Because I know you brought a piece of Libya desert last night.
There are a lot of materials, terrestrial materials that have been altered by impact. We call them impactites. Whatever the terrestrial rock that was run into ends up in some altered form. Now, in the Egyptian desert, it's called the Libyan desert, is in Egypt. this material is found. It's basically melted sand, and it's been on the ground a long time, 28 million years possibly, and it's had time to be thoroughly weathered by the wind action in the sand dunes, what we call benefacted rocks. So the shapes of these things are virtually just benefacted rocks, and they come in all kinds of weird shapes. But it's quite possible that there's never been a crater found that's associated with this, and for a long time we felt that it was probably an air burst. Something exploded before it got to the ground, like in Tunguska in Russia, that leveled that forest. There was never a crater or any material found, and the same could be happening with the Libyan desert glass. We don't know. I'm going to pass this around. This shows a picture of King Tut's breastplate, and in the middle of it is a scarab that was carved out of the Libyan desert glass, and then there's a sample of it here.
It's really, really pretty stuff.
Big, you know, you can find pretty big chunks. It's in the middle of nowhere. It's quite an expedition to go find it. But
Another bit of evidence of impact is something called shatter cones, and this is where the terrestrial rock has been deformed by the impact, and it forms this cone shape in the rock. You can
we call horsetailing.
You can see the geologist picked right here to get an idea of the size. This is about 3 feet tall, and these always point up toward where the crater was.
The point of impact.
Yeah, point of impact.
I collected at a remnant of a crater down just north of Santa Fe. There's no evidence of the crater in any of the geologic maps, except there's all these shatter cones. And I have pictures of me standing next to them. I wish I'd included one. The shatter cones are 8 or 10 feet tall.
They can range from a few inches in height to 10.
So I have a couple of those much smaller that I collected, and I got two different ones that I want to show you because I wanted to show you it can happen in any kind of rock. So it's you find these in the bottom of the crater. You don't find these in the top of the crater. The crater has to erode a long ways down to find shatter cones. But you'll see the horsetailing effect, and they always point towards the point of impact. So this one is
It's not really like the debris shot out.
this one's in some kind of schist, and this is in a piece of granite.
Just the shock of the impact distorted the rock.
You're talking about explosions that are bigger than any atomic bombs we've ever developed.
Yes.
Those are airbursts, right?
No, they're cratering units. They're cratering units.
This would be an impact. Okay, the last type of evidence is microscopic, and this is shocked quartz. You've probably heard of that. It forms either as a result of a nuclear explosion or the result of an extraterrestrial impact. And coesite is an example. This is a picture of it taken through a microscope, so you can see this at the microscopic level.
There are other forms of glass that are found in and around craters. What we call impact glasses. Pass this riper amount around. These are called egrizites. This is from a crater in Kazakhstan. These are not tektites, which we haven't talked about yet. Which tektites are blown away from the crater and they land in a strewn field, sometimes quite a distance away from the crater. These are found in and around the crater. Interesting, they're black glass, very interesting forms.
The difference between these and the tektites are where they're found?
Where they're found, yeah.
And that's all, but they're basically the same.
Tektites are blown way up into space and
they rain back down.
They land in a strewn field quite a distance away from the
So
crater.
they may be going through a different process if they get...
Right, they get blown way up into the atmosphere and way back down again. These are found in and around the crater.
How would you locate tektites in a stream field? You just kind of get lucky?
Yeah, I mean, strewn fields are mapped. In recent times, when there's a meteorite fall, the meteorite hunters flock to the area. We're now finding that we can use Doppler radar, weather radar. They found it leaves a footprint of the meteor coming in, and it's besides visual clues from people that have sighted it, in which we try to triangulate. The Doppler radar is even, gives you a lot more detail, and so there are guys that are working on that now. And when they pinpoint it down, boy, everybody flocks in, and starts hunting that field. And you put enough people in the field, you're gonna, if there's anything there, you're gonna find it. So people report where they find them, they take GPS, they take the readings, and map the strewn fields.
What about, was there one in Sudan or something a couple of years ago? They actually tracked a meteor coming in.
Oh,
Just saying.
about a Sicida.
Yeah, something
I'm trying to
like
remember the
that.
name. I've got 2 little pieces of it in the collection.
Yeah, there was one that the asteroid was tracked coming into Earth, and then it was seen as a meteoroid or meteor, and then it was found. There's only been one of those, and consequently, it's expensive.
2008, I think, is when they mounted the expedition to go find it.
Yes, students from the university in that country, fan out of the deserts, just literally big lineup.
It wasn't a nice place to go, so the meteorite people did not go there. It was
That
not a
was
safe
Ron
place to
Reed's
go.
trick, is you just get all the high school kids arm length apart and march across the dry lakes out in the
That's an interesting meteorite. It's got bits and pieces of all kinds of other types of meteorite composition in it, rather than just being one type. It's
Yeah.
well, kind of like, yeah. It's a pretty cool meteorite. But as Dan said, it's rare. It's also, they're also proud of it. All right, no discussion about meteorites would be complete without including some comments about meteor-wrongs. Dan passed around the mesosiderite-like native iron a little while ago.
I'll pass another round. This one was actually made as a fraud in Russia. You might think China, but Russia. This is called Cherkovsky, and somehow they managed to make a pseudo-palisite, olivine crystals surrounded by metal. They must have had fun pouring that all together and then slicing it up. But I bought a piece. Says in the back of it says "Made in Russia, 1992." So this is a very famous meteor wrong. It was actually an attempted fraud. So
Well, I've got a collection of meteor-wrongs down here. I'm not going to pass this around because these aren't attached. I like to use this in public outreach because you can pick up the specimen and then look at the label underneath. And I've got a nice collection of wrongs here, but there's one meteorite hidden in here, and the trick is to figure out which one is the meteorite. And I can assure you it's a lot harder than it
most geologists can't do it. I always have to laugh when people say, "Oh, I found this rock and I took it to the university and they said it was a meteorite." Most universities, most geologists, unless the thing fell on their head, they wouldn't have a clue. It is not something that is taught in geology departments anywhere. You have to have somebody that specializes in meteorites, and they're kind of few and far between. So when Jack Murphy was at the Denver Museum, he was an expert in meteorites. I don't know who you got there now that knows anything. You can bring material out to the School of Mines Geology Museum. I'm out there sometimes one day a week, and I get to look at a lot of rocks, and they're not meteorites. We could have put up this, we had this kind of joke Venn diagram that said, found a rock, is it a meteorite? And one arrow, and it just says not. So your chances of finding one are pretty slim. It has been done, but I think Jack Murphy was at the museum 30 years before he actually had one come in the door. And I've seen a lot of the stuff. I even had a guy bring me a lump of coal one time over to the geology museum. I couldn't believe it. He had wrapped this big thing in a blanket, and he went, ta-da, and I went, you got to be kidding me. So usually it's a lot more like a piece of slag, which is very, very common, meteor-wrong, or a piece of magnetite. I had one guy came in and he said, well, it's out in my truck and it's too heavy to bring in. I said, okay, let's go look at it. And he opened the door and I went, ooh, maybe. Turned it over and it was red on the other side. It was a piece of that iron. It was a glacial erratic from Canada, banded iron.
Yes.
Oh.
That's
So
a nice
it looked
iron.
very metallic on one side, but when you turned it over, it had the red the red hematite luck. So people ask me all the time, well, how do you know it's a meteorite? And I say, well, I look at it. And that sounds kind of flip, but when you've handled hundreds and hundreds of pieces, you know pretty much. And sometimes I can tell 10 feet away when somebody's bringing a rock in. I've had very, very few maybes. At the Geology Museum, if we have a maybe, then it can be put on an X-ray fluorescing spectrometer that we have, and I can tell you in 30 seconds whether it has any nickel in it. If it doesn't have any nickel, forget about it. There was a couple a number of years back that bought their first metal detector, took it out on the first weekend, and found a meteorite. Brought it to Jack Murphy. That was the one that he actually, that was a new iron meteorite found in Colorado, and they were very pleased, and I knew the couple, got to know them, and I told them that was such beginner's luck that you may hunt the rest of your life and never find one again, and that's generally the case. The guy called me a couple of years later at the museum and said, we found another piece in the same area. Went back to the same ranch. We found another piece. And we got kind of excited. We thought, oh, that'd be cool, find another piece. So they came in the next day and he handed it to me, and about this big, and I said, it's a maybe. I don't say that very often. So then it went to the spectrometer, and there was no nickel. It was a man-made piece of iron. So we were all disappointed. I had great hopes that we might have a second one from that area, but it was not to be. So
So the bottom line from this is, people think they've found a meteorite. 99.99999% of the time they have found a meteorite. And there are lots and lots of pieces of really cool looking magnetite, hematite, and slag and other things that are very common in Colorado. And we see these a lot, and they're not.
meteorites are not round. Meteorites don't have holes in them. Occasional hole, but not like volcanics, what we call vesicular rocks. So a lot of volcanics have a lot of holes in them. Meteorites do not. Meteorites are not round, hence the Moki marble. Meteorites are more commonly shaped, what we call pyramidal. Almost like you see in benefactor rocks. See the angles here? That's a classic form of a meteorite.
All right.
What is it that
They have
makes
fusion crust, and they don't really leave much of a streak on a streak plate, and they have nickel. So that's the primary. First of all, there's a magnet attached to it. Okay, you pass the first test. You can put it on a streak plate. Hematite leaves a very dark red streak. Magnetite leaves a very black streak on a streak plate, which is unglazed porcelain panel. That can be back of a tile or even the lid on your toilet. Turn it upside down, the unglazed portion. And that in mineralogy, we use streak plates for a lot of minerals testing. That's just one further test that you can use. Meteorites, you might get a little bit of streak at first, especially on an iron, to get the rusty surface off. And then after you streak a couple more times in the same spot, you get almost nothing.
What is it that's creating these classic lines and shapes that you're pointing out there?
I don't know, it's just the way the plate's coming through the atmosphere, things get like this. And if you look at the Mars pictures from the rovers, you see a lot of Mars rocks. They found a few meteorites on the surface, but you see a lot of what we call benefactor rocks, wind-shaped. And you'll see them on Mars, man. They just got big angles on them from the wind blows one direction one season and then switches around and goes another way. You can find them in Pawnee National Grasslands. A friend of mine's got a really beautiful benefacted piece from Pawnee. That's like, oh, I want to go find one of those. It's just really cool rock. So.
Is it a piece about that size that causes the fireballs to occasionally treat you?
The little fireball what?
The fireballs that were treated to sometimes, are they about that size when they enter?
Well, they can be even smaller. That's a pretty good sized piece. A lot of them are small when they land. A few of you have been around long enough to have known Larry Brooks, past president, who's no longer with us. And I wanted to bring this today. This is part of Larry's meteorite collection, so you get a chance to come down and look at it. He had more, but this was one really nice little box that he had. and come take a look at Larry's meteorites. I thought it was appropriate to bring those tonight. David?
A friend from work said he saw a meteor, he saw it land, him and his friends saw it land.
They always see them land.
They ran over to it, it landed in a schoolyard.
Yep.
He picked it up, took it home.
I'm sure.
And I said, you know, I'd like to see it. And he said, it's in my garage. And I said, bring it into work. He couldn't find it.
Nah.
Amazing how that.
Yes.
Yeah.
You got them crawled away.
Well, all the stories you hear of meteors striking the Earth and starting fires, that's all bull. It does not happen.
He said it was warm when they picked
They
it up.
could, it could be slightly warm.
More
But
often
when
than
you
not,
think
the-
about it, this rock has been traveling through space at near absolute zero. It enters the Earth atmosphere and in a matter of seconds comes through the atmosphere. The surface ablates off like an Apollo capsule. Is the Apollo capsule hot inside? No, it stays cool because the outside's ablating off. Same thing happens here. When this thing lands, it's still near zero, absolute zero cold inside. You know how people can't tell hot from cold? There's that old game where you tell them you put a coal in their hand, put an ice cube in, they can't tell. There's been frost found on meteorites after they land because the mass is so chilled inside. It never has a chance. The ablated surface is less than a millimeter thick on the fusion crust. It never gets warm inside, really.
All right, let's talk a little bit about Chelyabinsk and touch on collecting and then answer some common questions. We've got the questions and the answers here, and then we'll adjourn to Chamberlin for some refreshments. I have donuts in my car, so you guys have to follow me for the donuts. This time I brought 3 dozen. Last month I brought 2, and we ran out pretty quickly, so we got 3 dozen. Now, a little over, about a year and a half ago, you may remember seeing this in the news. Daytime meteor. You can see the airburst here. This happened the night before.
Why don't you kill the lights already?
Locally, well, it'll mess, well. All right, just the back switch.
Yeah.
So this was an object that was about 65 feet wide, entered the Earth's atmosphere going about 42,000 miles an hour, exploded 15 to 20 miles above the surface. The energy released by the explosion was roughly equivalent to 30 Hiroshima atomic bombs. The shock wave took a minute or two to reach the city of Chelyabinsk after the airburst, because people saw the bright flash, went to look, and then the shock wave arrived and it blew out windows in thousands of buildings. You can see people sweeping up the fragments. There were a couple older buildings that were knocked down, the walls were knocked down by the shock wave. And about 1,500 people were injured, mostly by flying glass. Now, what wasn't vaporized in the airburst continued on another 50 miles or so and then peppered the ground with meteorite fragments. The meteorite fragments, when I put this together, the largest ones were about this size. A lot of small ones, the little pea-sized ones, were picked up off the top of the snow. Since then, they found the one piece in the lake. It broke a scale at 1,200, 1,400 pounds. So it was probably around 1,500 pound chunk of meteorite from this meteoroid that entered the Earth's atmosphere. It has been officially classified. It is a stony meteorite. The classification is LL5. The LL means the iron content is very low. The 5, as Dan explained, talks about the chondrules in it, and in this case, the chondrule average size is 0.9 millimeter.
A lot of them would be deformed or not very prominent in a 5.
This because of the shock in that explosion, this is fascinating to look at under low magnification. We have a broken piece like this.
There's a lot of shock veins in this, but the shock did not occur in the Earth's atmosphere. The shock occurred in space and partially melted.
Right.
There are all these melt pockets.
The melt pockets are just
in this. It's really, you'll find particles that are just what we call melt. It has no chondrules. It's just black. It looks like a piece of charcoal.
Here is some of you have seen this before, but these are 3 little pea-sized pieces One of them is broken so you can see the inside, but as you look at this, let me turn the light back on. These have a jet black fusion crust on them. They're real neat little things. These were picked up off the top of the snow about 5 days after the event.
One of the Russian meteorite dealers, we were in Tucson when this happened at the Gem and Mineral Show, and he left immediately for Russia. And 2 weeks later, I saw him on a BBC broadcast. He had enough credentials. He was out there collecting. He was picking stuff up out of the snow. So.
As it happens, last month I was in Germany in a cute little walled city called Nordlingen, and they have a meteor museum because that city is in a
Built in a crater.
In a crater.
Oh, really?
And they had
It's a good-sized crater, too.
493 gram chunk of Chamberlin.
Nice.
And the church, the cathedral there is built out of impact-type rock.
It is, so you've been there, yeah.
I have not been there, but I know.
Oh, it's beautiful.
I have samples of the material.
It's really
I have a
fun
big
to look.
impact-type collection from craters all over the world of all over the rocks.
Well, I was on a paleontology trip, so this was just an added bonus.
Well, here's part of your paleontology. These are fossils that are found from the Reese crater. These are belemnites that were severely damaged by the shock wave and then glued back together, so they're all little tiny pieces offset.
Really?
How cool is that?
Yeah.
So there's your paleo.
Yeah, very nice.
I've also got, I was telling Ron, there's a crater in Spain where they found quartz pebbles that, because of the shock wave, all these pebbles, small rock, were jammed together, and I have this pebble about this big that has all these bruises all over it from that shock. And then I have a piece of conglomerate, and all the conglomerate pieces all have little bruises on them all over from the shock.
All right, as you can see, Dan and I are pretty enthusiastic about the subject of meteorites.
No.
We both collect them. It's a fun part of, well, it's kind of a mix of astronomy because it is related to space, but also geology. We also both collect rocks. And if you've ever had an interest in collecting meteorites, the first thing that you want to do is learn about them. And sitting through tonight's lecture is certainly one good way. But I would encourage you to check the International Meteorite Collectors Association website. They've got a lot of good links and information there.
If you ever buy on eBay, buy from one of the IMCA guys.
Yeah, look for
otherwise
this.
you might not have a meteorite.
I'll touch on that in just a second, but that's a very, very important point. Meteoritical Society also has good information on their website. There are several excellent books on the subject. They range from children's books up through PhD type university level books, and then there's just the general run-of-the-mill books for people that don't want to read research papers. So you can take your pick of all kinds of different books that will help fill in the background about meteorites. They're very, very good. Then you might ask, well, what kind of collection? Well, maybe a basic one. Maybe you start out with the three main types. You start out with an iron, a stony, and a stony iron. Say, okay, that's it. I've got those three types. I'm done. But if you're like many of us that get
There are
into
so many
meteorwrongs,
sub-levels, yes.
yes, you can buy a prepackaged collection like this one right here. It's a couple $100 from Jeff Nocton at Aerolite Meteorites, one of the meteorite men, and it's a nice way to get a nice little set that's labeled and everything's in nice little display containers, and it's a nice setup. Then you get into the serious stuff. Meteorites of different subcategories. Remember the classification charts that I showed on a couple slides? People like to collect meteorites from all the different subcategories. People like to collect meteorites that are location-based. For instance, there are 87-ish confirmed meteorites from Colorado. So people like to collect Colorado meteorites. There are a few that there are only one of, so never get them. They may be in the Smithsonian or in a private collection. Others, there are enough pieces out there that you can collect from many of the meteorites of Colorado. Falls versus finds. The falls versus the finds would be just walking around and find one. Very unusual, but it happens. The fall would be, all right, you see it, and then you go pick it up. Or somebody saw it and then it's picked up. The Chelyabinsk, for instance, falls into that category, fall, because it was observed. Hammerstones, that's an interesting one. Hammerstones, that's a nickname given to meteorites that hit something. The mailbox,
Some man-made object.
a car, a house, a barn, dog. Yeah, maybe. The interesting thing is that the vast majority of the time, the meteorites that are called hammerstones would otherwise be fairly ordinary and inexpensive, because they're usually an ordinary chondrite type meteorite or something like that. But because they hit something, the price tends to go through the roof. Not only does the price of the meteorite go through the roof, but so does the price of the object that it hit. The meteorite hit a mailbox. Claxton meteorite. I had heard that mailbox sold for something like $80,000.
The very famous Peekskill meteorite went through the trunk of a teenager's car. She was very upset until she found that she could sell that car and buy a brand new car.
Yeah.
For the money that she
Last
got.
I heard was
That car's still around. It's a museum. I knew the guy that owned it for many years.
Last I heard, it was owned by somebody in Idaho. I don't know if that's still the case, but the car is valued at about 25 grand. And it was a clunker old Chevrolet that was probably worth $300. And this poor gal came outside in the morning and saw the back end of the car all munged up and figured somebody
Clear
vandalized
through
it.
the trunk and into the ground.
And then she saw, oh, wait a minute, there's a hole here and there's a meteorite on the carport driveway underneath. So people like to collect those.
Go through the gas tank.
I think it just missed it. Thin sections, those are meteorites that have been sliced very, very thin and polished to 30 microns thinness, which
That's
is
part of
thin.
the classification process. It has to be a thin section.
They mount it on a glass slide, and people like to collect the thin sections. They're really, really cool to look at in a polarizing microscope. Impactites, Dan mentioned that he collects impactites, and of course meteorwrongs. Those are fun to collect as well.
My wife says, it's bad enough I collect meteorites. You collect meteor-wrongs too?
I do the same thing. I've got a small collection here. You know, it's fun to have fun with people and say, all right, find a meteorite in this box of meteorwrongs. Okay, where do you get it? You can get them at rock shops. They tend to be expensive. Online auction sites, as Dan mentioned, be careful. There are some unscrupulous dealers that peddle meteor-wrongs as meteorites, or they sell the very common ones as something that's very rare when it's not. So if you're going to buy online, and there are some legitimate dealers online, look for IMCA members. Online dealers, aerolite meteorites, that's Jeff Notkin of the Meteorite Men. I've bought meteorites from him. Impactica is here in Denver, that's run by